Welcome back to Chemistry 1510 video notes. We're going to talk about heat capacity today. So in this video, when we talk about heat capacity, let's really quick define what heat capacity is. Heat capacity is the amount of heat that it takes to change the temperature of an object 1 degree Celsius. And so when we look at heat capacity, which is going to be C, it's going to have units of joules or kilojoules per degree Celsius. So when we consider heat capacity as part of an equation, this is going to be our equation. C times delta T equals Q. So heat capacity is going to have that unit of joules per degree Celsius. We're going to see a temperature change, and then that's going to equal heat, which is in units of joules. So what you'll notice is your degrees Celsius end up canceling out, and so that's how we get the heat in joules here. So when we look at some simple problems that look at this relationship, we can first start with calculating delta T. And so in this problem, it says how much heat is required to warm an object that has a given heat capacity from 2.5 degrees Celsius to 10 degrees Celsius. The reason I want to take a moment and really break this down and calculate delta T is because it is very common for students to mix up significant figures here. Let's also remind ourselves that delta T is the difference in temperature. It's always T final minus T initial. So when we look at delta T, in this case, we're ending at 10 degrees Celsius, so that's our T final. And our T initial is 2.5 degrees Celsius. When we perform that subtraction, we have to keep our significant figure rules in mind to get 7.5 degrees Celsius as our difference. Now that we know our delta T and we've kind of put that in a different section so that we could focus on significant figures there, we can calculate the heat. So Q equals C delta T is our equation that we're going to use. When it says calculate the heat, it means we're searching for Q. We're given the C at 25 joules per degree Celsius, and then we just calculated the delta T up there. Now, in actuality, by the time you get to the exam, you don't have to do this kind of separate delta T calculation, but it's a good place to start until your brain is ready to look at significant figures of the delta T while it's in the overall bigger equation. So when we calculate this, we're going to round to two significant figures to get 190 joules. So we can use C, which is an extensive property, which means it doesn't depend upon the amount of the substance that's available. And then there's a slightly different version of C that does depend upon the amount, and that's called specific heat. So while we're talking about heat capacity, let's just transition into specific heat as well. So specific heat, oops, sorry about that. Oh, goodness. Specific heat is an intensive property, which means that it takes into account the quantity of the substance. So you'll notice that the unit for specific heat has a mass in it. So this is how much heat it takes to change 1 gram of a substance 1 degree Celsius. So we see specific heat in the equation Q equals ms delta T, and unfortunately, the chemists just can't keep it straight. And so sometimes what you'll see is people write this as Q equals mc sub s delta T, because there is such a strong relationship between heat capacity and specific heat that they put the C in there for some reason. And then some people do it really unusual. I don't even understand why they do this. Well, C is heat capacity. Specific heat is not the same as heat capacity. So I really don't feel like we should be doing that. It'll mix everybody up. So when we look at specific heat, it's going to have units of joules per gram degrees Celsius. So we're multiplying by our mass, we're multiplying by our degrees Celsius, and we end up with these canceling so that we get joules at the end, which is a heat unit. So let's look at this problem. It's a little bit more complex than the last one that we did. So it says how much energy is absorbed by a 5.5 gram gold ring, we're assuming pure gold, when the temperature changes 3 degrees. Now, if you weren't given the specific heat in the problem, you would have to go look that up. But we're given the specific heat in the problem, so we don't have to go search for it. Let's really quick calculate the change in temperature. Again, by the time you take the exam, you won't have to do this separately. I'm just doing it separately now so that we are capable of focusing on the significant figures. So when we do this subtraction, we should end up with 3.0 degrees Celsius. Now when we calculate the heat, we're going to use our equation of QMS delta T because we were given a mass in the equation and we were given a specific heat a mass in the problem and a specific heat in the problem. So we know that we're going to use Q equals MS delta T. So the mass that we're given was 5.5 grams. The problem also gave us the specific heat. And then we just calculated delta T so that we didn't mix up our significant figures. So when we go through this and we calculate our final answer, we should have only 2 significant figures, and our final answer is going to be 2.1 joules. So let's do one more problem together before we change topics. So this is a similar question, and instead of talking about a specific heat of a solid, we're talking about now a liquid. So we're talking about water. It says the temperature of 250 grams of water was changed 5 degrees. How much energy was transferred to the water? Great question. So let's write out the equation that we're going to use. We're given the mass and we're given a change in temperature. Because we're given the mass, that's going to lead us to believe we should use Q equals MS delta T. But you'll notice that the problem didn't give us the S for water. That's fine. We're capable of looking that up. So the specific heat of water is going to be 4.184 joules per gram degrees Celsius. If we look this up in different units, you'll also see that it's 1 calorie per gram degrees Celsius. Calorie is just another heat unit. It's similar to the calories that you see on the boxes of food, but these calories are actually smaller. The calories on boxes of food are technically kilocalories. So with this, we can take your mass of the water and put that in. I'm going to use the 4.184 joules per gram degrees Celsius because that's the one that our textbook seems to use most often. And then mentally, I'm going to do the delta T. Right? I know it's 5, but I also need to know the significant figures, and so it's going to be 5.0 degrees Celsius. When I put this in the calculator, it's going to give me 5,225 joules, which I will then round to only 2 significant figures because of my delta T. All right, we're going to stop there and pick up with heat sinks in another video. As always, thanks for your attention. This is Katoni signing out.